Next speaker is Kimberly Hambuchen. Okay. She's Deputy Manager for NASA's Human Robotic System Project and the Challenge Administrator for NASA Space Robotics Challenge. She has received her PhD from Vanderbilt, great university, and she's been a robotics engineer in software robotics and simulation division at NASA Johnson Space Center. She's an expert on human interfaces for supervising remote robots, and she has done a lot of development with our favorite, the Robonaut. Right? So with that, I will allow her to continue. You know how to use that?
I do.
Okay.
Okay. I need to apologize. I get really mobile when I present, so I'm going to try to bring it back here. I get to give the talk that Rob usually always gives. So I get to talk about the robots that we developed at JSC, show some really cool robot videos, and really talk to you about how this new center can be a big win for NASA Johnson Space Center. So, fortunately, Rob mentioned quite a bit of this. We really focus on human robotic systems at NASA, JSC. We leave JPL to do the science missions, and we focus on robots that can help crew out during future space missions. These are three main areas that we're kind of focused on right now for robotics. The first is something we call caretaker robots, and those are robots that we see managing resources when crew aren't around, when before crew arrive at, say, a Mars habitat or a deep space gateway. These types of robots will be taking care of things, kind of like Rosie the robot for a space station or a habitat. We're also looking at mobility for human crew. This includes lots of different types of mobile robots, rovers that human crew can drive, but that can also be driven remotely by a supervisor, mobile habitats to move the people around, and then scouting rovers that will actually do some of the science for the crew. And the third is human augmentation. And this is really all about taking robotic systems and augmenting a crew member, making them stronger, giving them more stamina, allowing them to do very difficult tasks, especially in something like a pressurized spacesuit, more easily so that they don't get worn out in a very short period of time. So this is really our focus, and we have lots of robots that we've developed at JSC that fall into these categories. As you can see, they all seem to have something to do with people. Again, this is our favorite picture in our branch at JSC. This is almost all of the robots that we've developed over the past 20 years, I guess. A couple are missing because one of our Robonauts is at GM, one of our partner building that. I believe we didn't have all of our Valkyrie robots in this picture. But this shows you an array of what we've done at Johnson Space Center. And some of these are what we call legacy robots. They're pretty old, and we've built newer versions, but we get to show them off. I will say that this doesn't have a laser, does it? Oh, it does. Our first Robonaut that we built is at the Smithsonian Air and Space Museum in Washington, D.C. I should put a picture of that in here. I forgot about that. So we're pretty proud of that. But this is just the vast array of caretaker-type robots, mobile robots, and quite a bit of human augmentation down here on the left. So I'm going to talk about several of these robots and show you some great videos, and then kind of talk about why this Center for Robotic Software is good for us. Okay, so first I'm going to talk about a couple of our caretaker-type robots. They are both humanoids, so they tend to attract a lot of attention, but we find that a humanoid form allows us to put robots into the humans world, not specialize the world for the robots. So we're pretty focused on that idea at JSC because we're building robots that will be interacting with crew in their own environment. So the first is Robonaut. I hope that most of you have heard about Robonaut, but if you haven't, this was our first, well, it wasn't really our first humanoid. I guess DART was our first humanoid, but it was the first humanoid I worked on at NASA. So we do have two different versions of this robot. Up here on the right, this was our first two versions of the Robonaut 1, and this one on the right is the one at the Smithsonian. This robot was designed to be a caretaker type robot, to do the sorts of things that human crew could do, but to put the robot into situations where it would be very dangerous for human crew to be there. We would like to let them do the very difficult things that also don't put them in danger. The more spacewalks that they do, the more chance there is that they could be hit by a micrometeorite, and we really don't want that to happen. So we do have multiple bases for both of these robots. Originally, we had, our first one was just kind of stuck on a base. It was our first attempt at building the Robonaut, but the second version had a single leg. We were looking at actually putting the robot onto space station. So we were trying out how could this connect to the outside of space station to go do maintenance type activities, the things that crew probably would rather not be doing because they like to do the very interesting things. And then on our second version, we have two different bases. We have this wheeled mobility base, which I'll talk about in a few slides later. And then we have two what we call climbing legs. We had an interesting journey with this robot. We originally built it thinking we could put this on space station. And then the Constellation program became part of NASA's endeavors. And so we started looking at planetary operation for this robot, which is when we decided to start using mobile bases. And then we kind of came full circle and were asked to put Robonaut 2 onto space station. So that's when we went back to designing climbing legs for this robot. So we do have what we call R2B is on space station. And I believe I had a video of that. Yes, so this is Robonaut doing some simple task panel operations, just showing the types of manipulation that this robot can do. And this is on space station before it got its climbing legs, so we had to send it up quickly and develop the legs afterwards. And one thing to note, we designed Robonaut 2 with General Motors. They were interested in how could we fit robots next to people, and we were interested in how could we make a version of Robonaut. So this robot was not designed to go onto space station. We actually had to make it flight-worthy after the fact. It's a pretty large robot. We probably would have gone a little bit smaller because it's pretty bulky for a space station, but we were able to prove out that we could get the robot up to space station and we could actually do some operations of this robot from ground. So once we actually had the robot up on space station, like I said, we started designing these climbing legs. And to keep it short, I'm going to move to the next video. So now we have this robot that has climbing legs. And we need to test everything here at JSC before we can do it on space station. So this video shows Robonaut 2 in our gravity simulator. It's the active response gravity offload system. And we can simulate microgravity in this system. So you can see the robot's in this harness that is offloading the majority of degrees of freedom. And the robot legs, as you can see here, have grippers, and they have a camera and a small, what we call depth camera, so it can detect depth, which is one of the main sensor features that we need to detect with robots. So it can find a handrail, and it can grasp onto the handrail. This is kind of our user interface that you can see. The main goal here was to have the robot climb to a location, grab this RFID reader, because everything on space station is tagged with RFID tags, so that it could actually scan for something that it's looking for. And this was about 2 years ago. So the majority of this was done under what we call supervisory control. The human is really in the loop here, and we're actually using the ROS ecosystem to do all of this. So we're using something called RViz as our user interface, our visualization guide. We're using something called Move It that is a ROS-enabled motion planning system. And really the human is kind of saying, okay, move your hand here. These are the areas where we want you to put your hand. This is how we want you to grasp things. And we're making sure that the robot, we think the robot will do everything we're asking it to, and then send the commands on. But the next year, we moved to something that is a bit more autonomous. So this is a video demonstrating the robot actually taking out cargo. Say, this is something that a robonaut could do at a deep space gateway while crew is not quite there. And this demonstration, again, using ROS to do all of this. This is a one-click, human says, here's your task, go do it. So we're actually using computer vision to find the objects that we need to grasp. We're using the motion planning, Move It software to do the motion planning on its own. The human is not saying this is how you need to do everything. The robot is actually figuring things out on its own. So we made pretty good strides there within a year to do some of these tasks that we think Robonaut would be doing. So you can see that, let's see, again, this is our RViz display, which is a ROS visualization tool. And you can see these little handprints. This is Move It planning to the locations where the robot needs to move its hand. And then this is, well, this is the video that's coming back from the robot that the operator sees. But the operator isn't really interacting with the robot at this point. The human operator is just saying go and monitoring data as it comes back. So you can see that we have quite a few applications for ROS with this robot. And we're very excited to actually see how we can use the Center for Robotics Software to further advance the autonomy for this robot. Because, again, the goal, the end goal for all of robotics probably is full autonomy, which is very, very difficult. And having a slew of grad students work on those problems is very useful to us. So our second caretaker type robot is Valkyrie. And this robot is we started development about 4.5 years ago. So this is a bipedal humanoid. It walks, it balances. So this is something that we could see managing habitats on Mars or on the moon, whereas Robonaut could be managing deep space gateways and zero gravity and space stations. This, I forgot to mention on Robonaut, so both of these robots have what we call sliding autonomy. We can either directly control them. Robonaut has a system that we call telepresence that allows a person to control the robot, and the robot will do all of the motions the person does. And we swing over to not quite full autonomy. We call it semi-autonomous operation. And Valkyrie is the same way. We do have multiple of these out in the world. We have partnered with some universities to do more advanced software development, and Court's going to talk about this, so I'm not going to go into a whole lot of detail about Valkyrie. But one thing I would like to mention is we developed this robot for something called the Darker Robotics Challenge, and we made some pretty huge strides since the first competition that we put this robot into. And you can see this is the robot in the competition trials, and then this is actually the redesigned version of the robot. We found out there were certain things we wanted to change, and so, for instance, we upgraded the sensor in the head. We have something called the Carnegie Robotics Multi-Sense SL, which comes with ROS drivers. So you don't actually have to do anything to get data from this head. There is a ROS package that you just pull down and bam, you're actually getting the data you need. So I do want to show one video. And this is my favorite Valkyrie video. So this shows the evolution of walking. We work with the Florida Institute for Human and Machine Cognition. They placed second in the DARPA Robotics Challenge, and their walking software is now on this robot. So this is kind of shows the progression of Valkyrie learning how to walk. And we just got some new video like yesterday, which was too late to get through the approval process to put in my slides here, but the robot is walking even better now. And so we're actually leaving this development to a not-for-profit institution that can do this very well. And they have ROS hooks into all of their controlling code. So again, we talk ROS to this robot unless we need to get under the covers. But yeah, so this was the first time we saw the robot walking much faster. And fortunately, I muted the video because I think there's a few expletives when people saw it walking fast for the first time. But this is one of the robots that we have. If you've ever come through the large, what we call high bay at JSC, where the space station mock-ups are, we actually have Valkyrie out there walking underneath her supportive truss so that everyone can actually see the robot when we're doing things with it. Okay, so the interest. Well, let's just finish this video because I don't think it's done yet. Court will have quite a bit more information about the robot, and this is one of our big collaboration robots that you know, we're getting a lot of use, or we're getting a lot of output from having these robots out in the world. So we find that this is, because we can't hire all of the people that we need, again, all of the grad students we would love to have working on these robots in-house, we find that shipping the robots out and having all the grad students work on them in their own lab has been a tremendous help. And so yes, that was the first time we saw the robot walking over something that was not flat, which was pretty incredible. Okay, so we also have quite a few mobile robots at JSC. And this is going to span probably over a decade of mobile robots. The first is the Space Exploration Vehicle. This is our large human rover. And while it is usually driven by people, this is also a robot. My background is in remote operations, remote interfaces for humans to control these robots. And so I've spent numerous hours commanding this robot from Houston while it was out in a desert in Arizona. And the idea is that we have something that humans can actually live in, can drive around, but when the humans leave, we can actually drive these sorts of things to a new location on Mars or on the moon when the next crew arrives. So we like to keep everything robotic so that we can still command all of our resources from the ground and then decrease the payloads that we need on each mission or each crew arrival, which decreases costs. And this robot can also do quite a bit of payload carrying. The video I have for this, I don't have the robot video. I have one of my interface videos because, you know, I think this is a lot more fun than watching the rover drive. Is it not playing? I thought I automatically played this one. Is there a way to, did you click the video? So, there we go, okay. So, this is one of the first interfaces we developed for operating remote robots. And you can see the middle, oh, I have this. The middle image is from a camera on the rover. So the human operator can see what the rover sees. And this image on the right this is really kind of the precursor to what we use now, the RViz visualization tool in ROS. This is a interactive way of commanding the robot, telling it where we want to go, and then we actually see the plan of where the robot should go in what we consider real time. We were mimicking remote operations, so we were always injecting time delays when we ran this rover robotically. So, and then you can see a lot of other stuff here. And we were working with JPL and the Ames Research Center on this project, and everything had to be done from scratch. All of this had to be developed by someone working on this project. But if we had had Ross when we were actually doing this project, we would have been able to get a lot more done because our visualization tool would have already been there. The image viewer would have already been there. Quite a bit of these other panels would have already existed for us to get the information we needed. So we could have actually done quite a bit more. So I'm a really big supporter of Ross because I grew up, or I went to grad school in the days before Ross when everyone had to develop their own software from scratch. And Ross is really enabling us to do a lot more with these robots. So I think that we're going to get quite a bit more advancement in, say, the next 10 years than we did 10 years previous to Ross. Okay, so our Centaur base is another type of mobile robot. We have our first version for the first Robonaut and the second version for the second Robonaut. These can also hold other types of payloads. So you see in this bottom right image, we have a bulldozer arm on the robot, so it can actually move dirt around on Mars or on the moon. And these also are remotely operated. Oh, I got a great video here. So this video is actually showing Centaur moving around at one of our field tests in Arizona. And in this video, we actually, I believe, had someone teleoperating the motion of the robot, but then the robot's going to go out and pick up a rock sample. And that was my task for that summer. And we tried to automate picking up the rock as much as possible. This again was before we actually had Ross. I believe later on in that summer, we did some testing to put Ross onto the Centaur base. Had a great intern do that for me, by the way. That was Stanley. He did our first Ross enabling of Centaur. So, but this is just video of how the robot can actually be used to do some scouting and sampling for crew without complete teleoperation. The robot found the rock itself, found the rock from a general area itself, and then moved its arm to that location, and then used its sensors in its hand to tell when it actually had hit the rock, and to close its hand and pull it back. And this is our latest rover. This is something called the Resource Prospector rover. The point of this rover is to go off and prospect for water on the moon. The ConOps for this will be remote operations on Earth. If we cannot have, we don't have processors that are radiation hardened, that are strong enough to do quite a bit of the vision and navigation work that we have now. We have such strong processors on Earth, but those have not been validated to actually go into, say, lunar environment and handle all of the radiation hits. So most of the navigation and computer vision would be done on Earth. And we have multiple payloads in this little rover. Have a pretty cool video of this out in our rock yard, doing some climbing around in very soft soil, so you can see it scooting around. We're working with Ames Research Center on this, and they are looking into actually verifying Ross for flight with this. We have yet to actually do that. Ross 1.0 is kind of an immature system for spaceflight. So we, I'll give it to them to actually go out and try to make Ross 1.0 flight compliant. But they are looking at whether or not they can do that, which would be a huge boom for us to be able to then go use Ross in spaceflight. I do think Ross 2.0 is going to be a lot more useful for getting certified for space. I will go with the caveat that we do not have Ross certified for spaceflight just yet. So let's see, let's make sure it gets out of there. But this, if we could send this off to the moon with ROS, that would kind of be awesome. And then students from the Center for Robotic Software could be writing flight software. Okay, a couple more human augmentation robots. So this is our X1 exoskeleton. And this exoskeleton actually ended up being something that we could use as a resistive exercise device for astronauts. It's small, it's compact, and they could actually build up bones with an exoskeleton. Whereas it can also be used as a rehabilitation device here on Earth, and we're partnered again with the Florida IHC, and so they were looking into that, and we were looking into how could this actually help the crew exercise. Unfortunately, this video is not playing, but you can go online and on YouTube and find the video yourself. We also have something called RoboGlove. This is a human augmentation glove, again, developed with GM, that is based on Robonaut 2 hand technology. And we can assist grasps in all types of situations. The grasp will hold position. So for instance, if we could put this in a spacesuit, then someone would be able to not have to exert force to hold their very pressurized spacesuit glove in the same position. Can also help manufacturers working on the line. So that's why GM was interested in it. And I've used this one. So this is just kind of showing you the operation of this glove. And you can hear the actuation whenever she closes her hand and opens her hand. Now, we have not yet gotten ROS into our human augmentation robotics. Because those devices are going on people, we have a pretty stringent set of rules for the software that needs to be on those types of robots. But I think I've already alluded to this a bit. How can this center actually help out with these robots? Oh, okay. So like I said, Robonaut 2 uses ROS. We have something called a ROS or ROCOS architecture. We don't use ROS for safety critical items or for real-time control. ROS does not yet have a real-time architecture, but we do use it for just about everything else. So our human supervisory interface uses RViz and tools that we've developed within ROS and within RViz. We use ROS packages for a lot of sensory processing. We have something we call supervisory control components, and these are really components that are kind of higher level, telling the robot what to do. Those all communicate using ROS. We use the Move It motion planning system, which is based in ROS. And we have a gazebo simulation for Robonaut 2. It's actually a public simulation that you can download yourself. But Gazebo is a dynamic simulator that natively speaks ROS. And we have that for both Robonaut 2 and for Valkyrie. We originally designed Valkyrie from the ground up with a ROS architecture, and a lot of the ROS architecture components were still in their infancy, so we had to kind of scale back on some of that. And IHMC has a different architecture that we had to pull in. But we developed our human supervisory interface on this robot, and then we have the gazebo simulation. And I think I have a video, yes. So this this kind of shows you, is this one not playing either? Could you click this one too? So this shows how powerful I think ROS can be. What we did with this video showing you is something we call affordance templates. I like to say we got a little too PhD with the terms that we were using. And this is showing you a RViz visualization view of the robot operating in a simulation. This was actually a gazebo simulation we were running. But you can simulate the sensors. So the robot is using the sensors that it has to actually see everything in its world. And you can see everything the robot sees in RViz, which is the ROS interface. And what we did was we took something called an interactive marker, which is, you can't see it very well against all of the green, but it's an RViz tool, and it speaks ROS. And we turn that marker into a template that actually can tell the robot how to interact with an object in the world. What an object affords, if you will. And this, I think, was one of the biggest things to come out of our, well, aside from the robot itself, our Valkyrie development, because this was something that we could go use on Robonaut 2. This is something we could go use on rovers. This is something that other people can use on other robots. And it allowed us to have this supervisory interface that makes it a little easier to operate some of these robots. So, the last thing I would like to talk about is the Space Robotics Challenge. This is something that we're doing in partner with a group called the Centennial Challenges at NASA. The idea is we would like to advance the autonomy for space robots. It is a simulation challenge. So we are providing a Valkyrie gazebo simulation. We are working with the Open Source Robotics Foundation, who maintains ROS and gazebo. They are developing the challenge simulation. Or they have developed the challenge simulation. And actually, tomorrow and Friday are the dry run days, and the competition occurs next week. But it's all in the cloud. So we don't have any really cool competition where people can cheer and get all excited. So Space Center Houston, who are actually the allied organization working with us to run the challenge, they're going to hold a very big event on June 30th at Space Center Houston. And we're planning on having as many of the teams that are competing come into town. We're going to show them around the JSC. And then Friday there will be quite a few different events. I have not gotten the final agenda yet from Space Center Houston, but I imagine they'll be doing some press releases about this. And they really would like industry that's interested in robotics to come out to this. They'd like to get people who are competing hooked up with some of the industry players. And we're going to have some good speakers talking about different things in robotics. So I encourage you, I wish I could give you exact details, but I can't, but I encourage you to keep an eye out. Check out Space Center Houston's webpage, because the more the merrier. We are planning on this being a pretty large public event. And, well, by the way, we have a ROS API that allowed this to happen very easily. Well, I'm not going to say very easily, it's been difficult. But we had the ROS API so that we didn't have to develop code for outside users to command the robot. And it works in Gazebo, so we had all the ROS tools ready to go for this. So I believe that's all I have. I hope I kept it to 30 minutes. But yeah, thank you. And again, we're really excited to have a group that's going to be working with ROS in our backyard, because as you can see, I think we can get a lot out of this collaboration.